what we're going to start with is taking a look at some series, which everything that we're going to look at now is going to be a geometric series. And we're going to try to determine whether those geometric converge or diverge. And if they converge, we're going to find their sums. What we're also going to make sure that we can do is, given a summation notation like this, be able to write out what the terms are, starting with the first term and going towards the infinite term, and just sort of write out what the series looks like. And we're also going to be able to take something like this, like 1 minus a half plus a fourth, etc., and turn it into its summation form. So just make sure we can write each of those things. So once again, let's remind ourselves what allows a geometric series to converge. If the common ratio between them, or the absolute value of the common ratio, is what lets the geometric series converge. If it is, if the absolute value is less than 1, right? If R is between 1 and -1, non-inclusive of those endpoints. All right, so here, it might help us out just to write this out to begin with. So we're starting at n equals 1. And so if we plug in n equals 1 to this, what is the first term that we get? We get a half to the 0 power, which is 1 times 3, which should give us 3. Everybody agree with the first term being 3?
Yes.
All right, when n is 2, we should get a half to the first power, which would be half times the 3, which should give us 3x. And the next term should be a half squared, so a fourth times the 3. And we'll notice that what's happening each time. The next term will be 3 over 8, right? And so on. So this is what this series looks like. It's the sum of 3 plus 3 halves plus 3 fourths plus 3 eighths forever. And so what is the common ratio between these terms? Should be a half. Exactly. Okay. So our common ratio is a half. And so we should be able very easily to figure out what the sum of this series is. This series should be equal to A over 1 minus R. And what did A represent? I should box that, but what did A represent? Yeah, A is 3 in this case. A is the first term. So this is 3 divided by 1 minus a half, R, right, our common ratio of a half, which gives us 6. And we know, and I should probably make a note over here, we know that this converges because the absolute value of R is less than 1, right? Everybody good with that? So this series, if you sum it infinitely, will equal 6. Good or no? Okay. And we will hopefully note here that when we had n equals 1, having n minus 1 here allowed us to very easily find that first term, because we're just going to a power of 0. And anytime we have the bottom here starting out as n equals 1, we want to make sure that the exponent that we're looking at is n minus 1 to make the initial term have a power of 0 attached to its common ratio. And we'll see that this right here happened to be our common ratio, right? The value that we were raising to n minus 1. So if we're ever looking at a summation that starts at n equals 1, goes to infinity, and it has some constant times some number to the n minus 1, As long as it's n minus 1, that thing in the parentheses that you're raising should be your common ratio, as long as there's no other terms in it. Good? Okay. What about this one? One minus a half plus a fourth minus an eighth and so on. And what are we doing? We're adding in negative a half to the n minus 1 every time. So where does this need to start at? It should start at n equals
1.
1, exactly. We're going to go to infinity. And the n minus 1 here is going to indicate to us that we want to start at n equals 1. What's the common ratio between each term? I'm multiplying each successive term by negative a half. So negative a half, and the power that I want to put on here is n minus 1. And we can note that that makes perfect sense, because if n is 1, n minus 1 is 0. Negative 1 half to the 0 gives us 1. And we go to the second power, that's negative a half to the first, which would be negative a half. Then we'll have negative a half to the second, which is positive 1/4, and so on. So this is what our series looks like. Our R value is negative 1/2. That's our common ratio. The absolute value of R is less than 1, which tells us that this converges. The first term that we have is 1. So this equals 1 over 1 minus our common ratio, 1 minus negative a half, which should be 1 divided by 3/2, which should be 2/3. For right now, yes, Aiden, we do need to say that it converges, because the specific question here is, does the series converge or diverge? If it converges, give it some. So yes, state that it converges. If it asks you that, oftentimes the question will just be, we'll just say, you know, does this series diverge? If not, find its sum or something like that. So just depending on the wording, but a lot of the time they will ask, does it converge or diverge? And if it converges, give it some. So just make sure you show that it converges, explain why, etc. All right, everybody good with those first two? I hope. All right, what does this series look like? We're going from k equals 0 to infinity, and k is fine. We can use k, we can use n, sometimes we use I for the values within here for our variables. Of 3/5 to the k. K equals 0 to infinity of 3/5 to the k. So let's write out what that series looks like. What does it look like? It looks like 3/5 to the 0, which is
1.
1, plus the next one would be 3/5 to the first, plus the next one would be 3/5 to the second, and so on, right? Forever. And what's the common ratio between the terms? R should equal
3/5.
3/5. If R is 3/5, we know that it converges because the absolute value of R is less than 1. Okay. And so it should converge to A, our first term, 1, over 1 minus R, 1 minus 3/5. That's a little bit better, which is 1 over 2/5, which is what? 5/2. Good or no? Easy enough. All right, what about this one? What should Is a always the first term in the series, or is it the coefficient in front of the 3/5? It's the first term in the series, Nick. A is the first term of the series. All right, so what about this one here? What's the common ratio here?
Pi over 2.
Pi over 2, right? And what does that tell us?
Does not converge.
That it does not converge. This must diverge, right? Because the absolute value of r is greater than or equal to 1. Right, so simple enough for that one. That one diverges. Good. Okay. Let's do some more. So this one, the sum from n equals 1 to infinity of 2 to the n minus 2 times 3 to the negative n plus 1 looks a bit more complicated. True?
Yes.
Yes. So the first thing we want to do with this is look at our starting value. Our starting value is n equals 1, which tells me that I want to have things within this summation to have a power of n minus 1. So our goal is to turn everything into a power of n minus 1. So we're going to start off with the sum from n equals 1 to infinity. How can I rewrite 2 to the n minus 2 so that the 2 actually has a power of n minus 1? I can't just do that, right? What else do I have to do?
Two times the power of -1.
Exponent rules tell me that 2 to the n minus 1 times 2 to the negative 1 is 2 to the n minus 1 plus negative 1, which is the same as 2 to the n minus 2. Everybody agree with that? I hope. Okay. What about the 3 to the negative n plus 1? That does not have an n minus 1, but how can I turn negative n plus 1 into an n minus 1?
Raise it to a -1.
I'm not sure what you mean by raising it to a negative. I can't just raise something to a -1 power.
Can't you do it 3 times the power of -n plus 1, then to the power of -1?
Oh, okay, I see what you're saying. To the power of negative. Yeah, I was gonna write it like this, but yeah, okay, I see what you're saying. Yes. Either way is fine. So you want to write it as this, n minus 1 to the -1, right? That looks pretty bad there, but 3 to the n minus 1 to the -1, right? Because that's how exponent rules work, right? If you have a power to a power, you multiply the powers. So -1 times n minus 1 is -n plus 1. And so what does that allow us to write this as? First off, 2 to the -1 doesn't have a power of n minus 1. We should just write that as a 1/2. We now have a 2 to the n minus 1. And we have a 3 to the n minus 1 to the -1. So that power of -1 tells us we should be allowed to drop that into the denominator. And then we should be able to rewrite this series as n equals 1 to infinity of 1/2 times 2 to the n minus, oh, I meant to do this all together, 2/3, that's why I was rewriting it, to the n minus 1. Everybody good with that or no? Any questions on how we got to there? Okay, and let's write out what this series looks like. First term should be 1/2, right? Second term, if I plug in 2 here, should be 2/3 times 1/2, which should be 1/3. So we got 1/2 plus 1/3. Next term, if I plug in 3, it should be 2/3 squared times 1/2, right? So 4/9 times 1/2, or 2/9. And each successive term, we'll note, is just getting multiplied by 2/3 now. So the next term is 4/27, and so on. And the common ratio between these terms is what?
2/3.
2/3. Our starting value, our initial term, our first term is 1/2. So this should be 1/2 divided by 1 minus 2/3, or 1/2 divided by 1/3, which is 3/2. Good or no? Any questions on that? Everybody's feeling okay so far? All right. Let's do this next one. So this one, because we're starting at n equals 0, we want to get everything up here to have a power of just n. So how could I rewrite -4 to the 3n? So that it just has a power of n on something.
Raise it to the 1/3 power. So -4 to the power 3n, then to the power 1/3.
Well, I can't just raise it to the power of 1/3 though, because that changes the entire nature of this thing. I can't just raise things to a power. I have to be able to rewrite this so that it's some number to the power of n. And so the way I should be able to do this is say, okay, this is -4 to the 3rd to the n, because that's how our exponent rules work, right? -4 to the 3rd to the n is the same as -4 to the 3n. So that's going to allow me to simplify what's inside of the brackets and then just have it raised to the power of n. Everybody see that? Good or no? With the numerator part? Okay. And how do I turn 5 to the n minus 1 into something that has a 5 to the n? If I write 5 to the n there, that's fine, but what else do I have to multiply that by? 5 to the -1, exactly. As the exponent rule says, same base, add the exponents, n plus -1 gives me that n minus 1. So we should be able to rewrite this then as the sum from n equals 0 to infinity of, well, let's see, 5 to the -1 doesn't have a power of n, it's just a constant. So we'll put that as just a 5 because it's a 5 to the -1 in the denominator. And then -4 cubed is -64. and that's to the n, and 5 to the n should be negative 64/5 to the n. Everybody agree with that?
Yes.
All right. So what is the common ratio here? What am I going to be multiplying each thing by? Each successive term. Negative 64/5, exactly, the thing that I've raised to the nth power. So r equals negative 64/5, which tells us that this diverges because the absolute value of r is greater than or equal to 1. Good or no? And we'll go back up here because I told Aiden earlier, I should have said that it converges. So that one converges because it says, does it converge or diverge? Did I say that for the other ones? Oh, good, I did. All right. Everybody good with those 5 or 6 problems that we just did? I guess 6 of them that we just did. Feel like you could do some of these on your own? I hope. Okay. This, so you'll have one assignment tonight that is solely based on this, taking a geometric series and determining whether it converges or diverges and finding the sum if it converges. So it's one thing that you'll be doing tonight. So now this is all great, right? This is all fun stuff. We got some cool little series of numbers that we can find sums of, and some of them we can, and some of them we can't. And you know, there's some cool things about it, and it's neat. But what's really the point of all this, right? That's what we need to get to. So let's take a look at if we can adapt this idea of a geometric series to a function. That's what we're going to be talking about the rest of this time today. So we are going to say that we have a new geometric series that is represented by the sum from n equals 0 to infinity of just x to the n power. All right. So that series should look like x to the 0 plus x to the first plus x to the second plus x to the third, and so on. And this is clearly a geometric series. True? Did you all agree with that? The common ratio between the terms is? X, exactly. Okay. So that would tell me that if the absolute value of my common ratio, x, was less than 1, this series should converge to something, right? And it should still converge to a over 1 minus r, because this is still a geometric series, right? If this is true, if x, absolute value of x is less than 1. And so if r is x, what is a? A should be our first term still, which is 1. And so if x is between -1 and 1, this series 1 plus x squared plus x cubed plus x to the 4th and so on should be equal to what? Exactly, Luke. It should be equal to 1 over 1 minus x. And that's exactly what this series equals for x values between -1 and 1. Okay? We call this thing a power series. This power series is centered at x equals 0. the reason that we say it's centered at x equals 0 is because the interval of convergence is -1 to 1, and the middle of -1 to 1 would be 0. Now, what does that mean is the question that we've got to sort of explore here. In order to do that, we're going to take a look on Desmos for a minute at what this really looks like. So we're talking about the function 1 over 1 minus x, right? That's this function right here. True? You all are familiar with this function? And I really only care about it between -1 and 1. So I'm going to, okay, that's I'd like to get a little more of that. I'd like to get up closer to 1. Let's just look at it like this. That'll be fine. -1 to 1. We know it's going up to an asymptote there, right? It's definitely got the vertical asymptote there. We're going to look at it like this. You all can see Desmos, right? I showed it on the Desmos, yeah? Okay, cool. So what happens if I start typing in this series? Well, my series starts off with just 1 as the first term, right? In fact, I'm going to have to put equals 1 there. Else it won't let me do this. So y equals 1. Does y equals 1 look like 1 over 1 minus x between -1 and 1? Does it? No, it doesn't, right? It doesn't look like 1 over 1 minus x. I mean, it does at one specific point. It looks exactly like it at x equals 0, right? But other than that, it doesn't look much like it. What if I put in the second term? Does it look more like it, at least? Maybe not like it at all, really, but does it look more like it? Somewhat more like it, right? There is, I mean, at least it's now going, it's got a positive slope now rather than a slope of 0, right? Okay, well, what if I put in the next term? How about now? Does it begin to resemble between -1 and 1 more like 1 over 1 minus x? I would argue that it looks more like it now. Yeah, a little bit more. Yeah. All right, well, let's put in x cubed. How about now? Looks more like it or no? Yeah. And what if I put in x to the 4th? More like it? And x to the 5th? And x to the 6th? And it just really starts to line up more and more and more and more along this same curve, 1 over 1 minus x, on the interval from -1 to 1, which is pretty cool, don't you think? It's very cool, that's right. What would happen if I were able to put an infinite number of terms here? Well, if I could put an infinite number of terms into Desmos, it should look exactly like 1 over 1 minus x everywhere between -1 and 1. And so obviously we can't put in an infinite number of terms, but what we can do is we can at least use in Desmos, they've got the nice little summation formula here. And we're going to go from 0 to, oh, we'll type out the function first. It's just x to the n. Right? I think I need to put in y equals here in front of this. And how high do we want to go? We started at like 6 or something, right? Or 7. That's how many terms we had before. Let me get rid of this. So we had about 7 terms in there, and it looked pretty darn close, right? Well, what if we put in 10 terms? Still looks pretty good. What if I put in 100 terms? Let's see if Desmos can handle 100 right off the bat. It's going to lag for a minute and maybe be able to do it. Or maybe not. Oh, there we go. There's 100 terms. Took it a second there. And it's gone all the way down here to negative 0.949, right? Is where it then shoots back up and is no longer like 1 over 1 minus x. And we could see, you know, we could follow it along here. And man, it sure looks just like it over there, doesn't it? And I don't know how much Desmos could handle on here. But maybe if we give it a 300 there. We were intersecting at 0.949. So let's see if we'll give it a second here and see if it can adjust that or not. $300 might be too much for it to handle in its calculations, because you got to think it's, what is it having to do here? It's having to do x to the 0 and then x to the first and then x to the second and x to the third for every value between -1 and 1 all the way up to the 300th power of each of them, right? And it's really struggling here. But we'll give it a second. But you guys sort of get the idea that this is going to look exactly like this function. It's going to be that function if we had an infinite number of terms. Isn't that neat? Don't you find that just really cool? I think it finally did. Yeah, I made it to negative 0.97. So I got a little bit better with 300 terms. And 300 is such an insignificantly small number. Imagine if we put in 100 billion, which is also such an insignificantly small number. Right? But pretty cool, right? And it just goes from looking pretty close to just getting better and better and better with each larger number I put in there. Right. Good or no? Good or no? Are you all really impressed?
That was impressive.
Yeah. It's going to get even more impressive as the unit goes on. We'll see some very, very cool stuff. So that's power series. A power series can be centered at x equals 0, or it can be centered at some other value a. So ours was centered at 0, and it had an interval of convergence from -1 to 1, right, which is how we knew it was centered at 0, because 0 is between those. And it means that as we go towards infinity, that series resembles that function on the interval that we're given. And so the same thing would be here. We could have one that's centered at x equals 1, and it might converge from 0 to 2. And so we'd be able to look at the function from 0 to 2, and it would look just like our series. And so we can have a constant attached in front of the x to the n if we wanted to. So like I could have put a 2 out in front of there. And if we had a 2 out in front of there, our first term would have been 2. And so we would have had 2 over 1 minus x would have given us this. We would have a function that modeled 2 over 1 minus x if we had a 2 in front of each of these terms. Or I could have turned it into x minus 1 to the n power. In fact, maybe we should look at that on Desmos. And I could say that it was then centered at 1. It would go around 0 to 2. And we'll do that actually right now. So if I had thrown in, maybe we won't do the x minus 1. Let's just throw in a 2. 2 times x to the n. And if we're going to do this to, let's say, 5, then we just need a 2 up here. We can see that we should be still converging -1 to 1 because this 2 is just a constant in front, and it just put a 2 up here. Everybody see that? The higher up where we go, the better it begins to resemble it. Good or no? And do the same thing with a 3 if I want to, right? Now it's up at 3. If I wanted to, I could make it a -1. And we'd see that same thing, -1 to 1, it's going to overlap it. Everybody good there? So centered at 0 just means that the middle of the interval of convergence is 0, Nick. That's all that means. Okay, and so we were also saying that we could have thrown in and made this x -1 here. So let's do that real quickly. X -1 to the n. Well, then I would have to turn this into an x -1. And obviously that could be simplified, but we'd see that then our center here, right, our interval of convergence is going to go from 0 to 2, and we're centered at 1. So it's now lining up pretty well from 0 to 2. But after that, it doesn't line up. Right? Good or no? Any questions there on that? Okay. And so if we were to look at this power series centered at x equals a, what is our common ratio between the terms here going to be? Should be x minus a, right? Each time I'm squaring and then cubing and then to the 4th and to the nth power to this x minus a. And so we should be able to say, since this is just a power series, and since power series is just a geometric series, it should converge for when the absolute value of r, or the absolute value of x minus a, is less than 1. And so that could be rewritten as x minus a is less than 1, greater than -1. And we would then see that the interval of convergence was a plus 1 and a minus 1. Okay. And so that's how we would know that if we put a 1 in here, we'd have it centered between 0 and 2. Is that good? Okay. Hopefully that's all good, because if that's not all good, we're going to have some problems because it's going to get exponentially more complicated. Everyone's good, I assume, since no one's saying anything. All right, let's see if we can find a power series to represent 1/1 plus x on the interval from -1 to 1. So we did 1/1 minus x, that was easy enough. We want to try and do 1/1 plus x. And so what's the only difference between 1/1 minus x and 1/1 plus x? This is an easy question. The difference between 1 minus x and 1 plus x is the plus instead of the minus, right? The difference between the one we just did, 1/1 minus x, and 1/1 plus x is that sign, right? Yeah. Well, what we're going to do is we're going to try to rewrite this in a form that looks like 1 minus something, because this thing down here is just our r. This is just our common ratio. And so I can replace this x that I had in the one way back here, right, with any function that I want. And if I replace it with whatever function I want, that function just becomes my common ratio. So what function do I need to replace with to give us a plus x there. Should just be a negative x, exactly. Perfect. So that tells us that our first term, a, is still 1, and we now have a common ratio of the opposite of x. And we should be able to write this out as a series. This should be the series from n equals 0 to infinity of just our common ratio to the n. Or if we wanted to, we could also say -1 to the n, x to the n. And often we'll see series written out with a -1 to a power times some other thing to a power. And sometimes we might make this, -1 to the n plus 1. If I made this -1 to the n plus 1, instead of starting with a positive term, we'd start with a negative term for a power series. But let's write out, what does this series look like? What's the first term of this series? Should be 1, right? That's what we already said. If I plug in 0, negative x to the 0 is 1. Second term, if I plug in 1, should be minus x. What should the second or the third term be? Or I guess, what should the term at n equals 2 be?
X squared.
Squared, and then the term at n equals 3 should be a minus x cubed. And then a plus x to the 4th, and a minus x to the 5th, and plus x to the 6th, and so on, right? And so we would hope that this series should model 1/1 plus x from -1 to 1. So let's see if we've done this correctly. So 1/1 plus x. Right, looks like this. And if we want to put in our summation, let me add, if I just type sum, it'll do it. So we're going to go from n equals 0. And let's just start at like 5 so that Desmos doesn't struggle. -x to the n. And it sure looks like even at 5 terms here, or 0 to 5, so 6 terms, it looks like we're doing a pretty good job of modeling that function. I pump that up to like 50 and give it a second to evaluate it. And it looks really, really accurate along -1 to 1. It looks like we've done this correctly. Good or no? Cool. All right. Let's see if we can do another one. So let's see if we can find a power series to represent x over 1 plus x from -1 to 1. Any thoughts on how we might do this? Factoring 1/1 minus x. Now it's much less complicated, actually. X over 1 plus x is the same as the one we just did, except it's just been multiplied by x, hasn't it? There's a very cool thing about power series that we will eventually spend a fair amount of time talking about. But if you have the power series for 1/1 plus x, you can just multiply every term in it by x, and it should give you the series for x over 1 plus x. So a second ago, what did we have? We had, for 1/1 plus x, we had the sum from n equals 0 to infinity of -1 to the n, x to the n. So let's write out that 1 over 1 plus x was the sum from n equals 0 to infinity of negative 1 to the n, x to the n. Well, what do I need in there? I just need an x to be added into that, right? So could I do n equals 0 to infinity of negative 1 to the n, x to the n plus 1? Would that do it? That's just this series multiplied by x. Or we could shift this index, is called an index. We could shift this index up to a 1. And if I brought this up to a 1, we could call this the sum from n equals 1 to infinity. We have to drop each of these ones down. Negative 1 to the n minus 1. And then it would be x to the n. Either of those would work. And what would that series look like? What's the 0th term here, or the first term here? Should be x, good, yeah. So we got x, and then the next one, if I plug in n equals 1, it should become minus from this, x squared. And then the next one will be positive 1 times x cubed, minus x to the 4th, plus x to the 5th, and so on. And so the hope is that between negative 1 and 1, that should resemble x over 1 plus x. So let's put in an x here. Let's get rid of this. And we changed it to, let's see, we had n equals, what do we have? N equals 0, and we had negative 1. What do we have? We had negative 1 to what power? Right, negative 1 to the n, x to the n plus 1. Isn't that what we had? And if we put a 10 on there, let's say, sure looks pretty close from negative 1 to 1 already, right? Put 100 on there, and it's going to look even better eventually. And it's still converging around negative 1 to 1, because the common ratio between them was just that x value, and the absolute value of x has to be less than 1. Good or no? The other form of the summation, oh, how I shifted the index? Yeah. Yeah, so you can shift the index of any summation. So like if this was n equals 0, you can always shift this up by 1 by reducing the power of everything in it by 1. Or you can shift down from 1 to 0 by shifting every power in this up by 1. So if our index goes up 1, then all the powers go down 1. Which could be helpful too sometimes if we started like, having an index of 2, we might want to shift it down to n equals 1, which would mean we would just shift all the powers up by 1. All right. We still all surviving this? Everyone feeling okay?
Yes.
All right, spectacular. Let's do another one. Let's find a power series to represent 1 over 1 minus 2x on the interval negative 1/2 to 1/2. Shouldn't be too bad, I don't think, because 1 over 1 minus 2x looks a lot like 1 over 1 minus x, right? This looks just like a is equal to 1 with an r value of what's the r value? This is a over 1 minus r, right? So yeah, 2x exactly. And so we know that this, the series that we could write out for this, which should look like the sum from n equals 0 to infinity of our common ratio, 2x, to the n, which looks like 1 plus 2x plus 4x squared plus 8x cubed, and so on, should only converge for the absolute value of 2x is less than 1, which would be 2x is less than 1 greater than negative 1, or x is less than 1/2 greater than negative 1/2. Right? And that's the interval that we were talking about. This series, 1 plus 2x plus 4x squared plus 8x cubed, and so on, should look just like 1 over 1 minus 2x, but only on this now condensed down interval of convergence. Still centered at 0, but now it's just a smaller interval in which it converges. There's 1 over 1 minus 2x. And we had 2x to the n. And if we put in 5, let's say, looks pretty good, right? Put in 50, we can see that once it finishes doing it, that right as we're going to get to here at about negative 1/2, it skews off wildly away from it, right? Because our interval is only up to negative 1/2 to 1/2 now instead of negative 1 to 1. Good or no? All right. So this is one that we actually already sort of looked at something very similar to it. Let's see if we can find a power series to represent 1 over x between 0 and 2. So the question then becomes, how do I rewrite 1 over x so that it looks like a over 1 minus r? So what can I do with 1 over x? It looks like 1 over 1 minus something. Yeah, 1 minus x sounds good to me, Aiden. Okay. 1 minus the 1 is 0, and then the negative x is a positive x. So that would tell us that our r is 1 minus x. Our common ratio should be 1 minus x. And we want to make sure that that gives us this particular interval that was requested, 0 to 2. So take your common ratio, put it in absolute value, set it less than 1. and solve the inequality. Subtract the 1 gives you a -2. And then divide by a -1 will flip your signs. And it shows us that this series, or this function, can be represented with a power series for 1 over x on the interval 0 to 2. And since this is what we ended up with, this is just the sum from n equals 0 to infinity of our common ratio to the power of n. Good or no? And there's 1 over x. And we're talking specifically 0 to 2, so we got that on here pretty good. And we want the sum from n equals 0 to, I don't know, how high you guys want to go on this one. How about at 5? Looks pretty good. How about at 50? In a minute, it's going to look even better. Right? And it looks like it's matching up really nicely from 0 to 2. Any questions there? Any issues with that? All right. Let's see. Nick, the answer is the summation notation, not the list of terms that you would write out. Yeah, I mean, it's particularly for that one, the terms look really annoying, right? If we were to go back to this, the first term is 1 minus x to the 0, which is just 1. The second term is plus 1 minus x. And then the next term is plus 1 minus x squared. So I mean, if we try to distribute everything out, it's going to look like a giant mess. But this summation is the answer that we're looking for, this series right here. All right, let's see if we can do this one. Let's see if we can find a power series representation of 1 over 3x, and then figure out what the interval of convergence is for it. So we need to be able to rewrite 1 over 3x as 1 over 1 minus something. And what should that something be? Yep. There is 1 minus 3x. Okay. Which tells us that this series should be the sum from n equals 0 to infinity of 1 minus 3x to the power of n. And we're also asked to find the interval of convergence. And so we need to take our common ratio, put it inside absolute value, and make it less than 1. So 1 minus 3x is between -1 and 1. We'll subtract. And what do we end up with here? We end up with x is greater than 0, but less than 2/3. So if I were to graph 1 over 3x and the summation 1 minus 3x to the n from 0 to infinity, they should look exactly like each other on the interval from 0 to 2/3. So let's do that. 1 over 3x. And our summation became 1 minus 3x to the n. And between 0 and I don't know about here, probably 2/3 once this finishes populating. And it looks real good between 0 and 2/3. Good or no? Any questions on that? We're almost done with what we're going to do today. So let's see if we can find the interval of convergence and the function that is represented from those two geometric series. And these may be ones that we might have already looked at a little bit today, but let's see if we can rewrite both of these so that they look just like a common ratio to the power of n, since we're starting at n equals 0. So for the first one, we should be able to rewrite this as a sum from n equals 0 to infinity of 2x to the power of n, which tells us that the common ratio is
2x.
2x. And so this should be equal to 1 over 1 minus that common ratio, 1 over 1 minus 2x. And the absolute value of 2x has to be less than 1. And x would be between -0.5 and 0.5. So here's our interval of convergence, and here's our function that is represented with that series. Good or no? And what about this one? How would we rewrite this? This would have to be rewritten as the sum from n equals 0 to infinity of, if we throw a -1/2 in there, that would become a 3 minus x over 2 to the n. And so now we can clearly see the common ratio between each term of this one. And we should be able to say that this should then equal the first term, 1 over 1 minus 3 minus x over 2. And with any luck, we can simplify that down, right? We can make this 2 over 2. And then we can take the reciprocal of that, right? Which gives us 2 over, and then we're going to have 2 minus 3, which will be a -1, and a negative x, which will be a positive x. So we have 2 over x minus 1 should be the function that this series represents. And we should be able to take the absolute value of 3x minus 2 and make it less than 1. And that would give us what? -2 and 2 and -5 and -1, and x is greater than 1, less than 5. Does that make sense to everybody? And I believe we already did this one, 1 over 1 minus 2x. So let's take a look at this one in Desmos, and then we'll be done for today. So we had the function, what was the function? It was 2 over x minus 1 is what we came up with. And our sum, I believe, from n equals 0 was 3 minus x over 2 all of that to the power of n. Does that look right? And let's just say 30 or something like that. And it sure looks like between 1 and 5, that is very similar, right? Good or no? Any questions?